Okay, the African coastline here, one of the largest east, north to south coastline in the world. And you say, why is it shaped like that? According to the Pangea model, people say it's because the continents fit together. Well, if that's true, then why is the North Atlantic rift spread bent like this? Why isn't it straight? Well, the expanding Earth people, they would say that if the Earth was smaller, it would all fit together, and as the Earth got bigger, gained mass from somewhere or nowhere, it spread apart. Well, this shape right here is also this shape right here, which, if you use this as the spread point, stuff coming out of the Earth and spreading in these two directions, this is also the shape of the African continent, which also this side of the Americas is approximately the shape of Africa, but since this is moving north, it's, if you shove this down, you'd have a more accurate Africa representation. But continuing around the continent across the Pacific plate, you can see that this also is in the shape of Africa. And at this point, any movement to the west is going to be subducted in the southern hemisphere into this trench system, and on the northern hemisphere side, it's subducted in these areas. So the south must not be moving, so the north is pushing over into Americas. The America pushes on the Pacific plate subducts here. So you say to yourself, why isn't more going down there then? Why isn't this moving over also and subducting equally there? Well, as it spreads out from the South Pole Antarctic spread area, which incidentally you can see the American rift, the North Atlantic rift, the African rift, the Madagascar, over to the Indian Ocean rift. You can see from this area, it also comes out into New Zealand, Australia. So you see the emanation of crustal material from the south. And so if this was straight at one time and the Pacific plate is diving in here, you could see how this would push and flow over that way, while this remains more stationary, because as it spreads up, once it gets to the equator and crosses the equator, it starts to compress. Everything backs up on itself, and yet you still see it moving this way. So why is this staying stationary? It is because old Africa could possibly have been Europe and India, as it travels up north going this way. But as it's traveling towards the east, the southern hemisphere African flow meets the now coagulated northern hemisphere flow. They're flowing together like this, and here comes the Australian flow. And so it's like three glaciers coming together. They twist around like this and subduct into the trenches over here. So where these three meet, this, and this, you have the Alps, the Himalayas, largest mountains in the world. And they, again, go over this way to trench. So at Japan, that region here is where these three flows pretty much come together and trench down. So Japan has a lot of crustal surface tension pushing in this general area, so it gets a very large amount of earthquake material activity. So recently we saw the New Zealand earthquake. We've seen the Chile earthquakes, and looking at this as your reference arc, if you come over and look at the Haiti earthquake, so it'd roughly be here, here, so you roughly here, a little below mid-arc, is where this recently developing fault has occurred, in which South America comes up and shoves over, heads up this way, with New Zealand and Chile and Haiti. Also, these push the plate up, and there's been some big earthquakes up here like 1964, which takes pressure off here, allowing more pressure or movement to come here. But coming across from Haiti, you see Indonesia and their big earthquake. So then the South American, the Pacific plate moves up, Haiti pushes this way, Indonesia moves. Now there's a lot of pressure to where Japan kind of twitches over that. So in predicting earthquakes, you look at big events and how, if we have a movement over here, it's going to affect over here, and a series of movements can affect and change the torsion equations on the overall whole of the planet, to where you can predict that a big event would occur here or there or wherever, based on the various earthquakes that have changed the pressure loading equation on the planet. Like the 1812 earthquake changed the fault line along here, the Nova Scotia, St. Lawrence River, New Madrid earthquake fault line, which is thought to be extinct unless things speed up, and things don't have a time to move plastically. You could have tearing and rupturing here, which probably would sound like big explosions in the region from here to here, which people have heard. And that was 1812, they had the big one there. 1964 in Alaska, 1700 in Cascadia, which also sent large tsunamis over across the Pacific Ocean. It was recorded in Japan, local legends in the Northwest area. And so looking at all recorded history as a baseline of where movements are occurring and how each time something moves, if something moves here, it reduces the pressure here, increases the pressure there. Or if something trenches down, you now have less pressure here, which means something can move there. And that's where you have a structural stressing and loading of the planet's crustal structure. And it moves systematically, it moves routinely. And so that's all this landmass comes up here. A lot of it trenches in, a lot of it has become stagnant and sat here for a long time. In Iceland, and I believe there was a big hot spot downdraft in Siberia, where when the land starts to squish enough it liquefies and goes down. Yellowstone has a large supervolcano. If it was an Audi instead of an innie, it would be this massive volcanic cone which would rival or exceed the Hawaiian Islands. This is an Audi, this is an innie. This is an innie, a downdraft or outdraft. So outdraft, indraft, indraft. They say the Great Lakes might be a downdraft. I don't know. It's possible underneath all that limestone that was deposited by the seas. If you were to take a look at the volcanic bedrock crustal area, who knows? But like our atmosphere, there's a lot of mixing of various densities of materials. Otherwise, you'd be able to start at the periodic elements with the lightest gaseous elements at the very top, your heavier gases on the bottom, to your lighter materials, liquids in the middle, all the way down to your most solid, heaviest elements. It's not the case. There's a lot of mixing of materials and flows. Following the laws of magnetic flux, the crust follows the flux field flows, which that combined with convection currents moves a lot of the material of the earth, mixing it up. That's why we have gold next to iron sulfide, fool's gold. One's very light, one's very heavy. Why are they both at this strata of the planet's spheres?